We are switching over to the next presentation that we have, and DESY. DESY is one of the world's leading accelerator centers. Researchers use the large-scale facilities at DESY to explore the microcosm in its all variety you can imagine, from the interactions of tiny elementary particles and the behavior of new types of nanomaterials to biomolecular processes that are essential to life. So all spectrum you can imagine. So my pleasure to give the floor to Hans Christian Wille, group leader of FS-PETRA-S experiments, Deutsches Elektronen-Synchrotron, DESY, Germany. So the floor is yours, Hans. You should switch on microphone or something like that, because you're extremely silent.
My microphone is on. Can you hear me?
Okay, everything's fine now. Some kind of glitch in the system.
Okay, yes, thank you very much also to the organizers to giving me the opportunity to give you a little overview about what we are doing, especially at the P21 at DESY. It's, as you have already heard, the DESY campus is rather large and accelerator campus with a long history, and we actually having quite some experience in building accelerator facilities, and we are sharing the campus with many cooperation partners on site. As you already heard, we are starting to accelerate the electrons for the European XFEL. We have our flash laser, the soft X-ray laser on site, and of course one of our working horses is the PETR4 synchrotron radiation source, which you can see here indicated in blue. Many people are contributing to this, and also stakeholders, shareholders with own Beamlines. I should mention the cooperations with the University of Hamburg, the Max Planck Society, the European Molecular Biology Laboratory, and the Helmholtz-Zentrum Geesthacht. And also we have a few partners, international partners like Sweden, India, and Russia, who are invested in our initiatives. So this is the outro of my talk. I'm just going to briefly show you a little bit about the features and scientific scope of PETR3 and also PETR4, our future source. I will give a few research examples also, and then have an outlook to our project PETR4 in the end. So here's the fact sheet about PETR3. This is actually a rather old synchrotron already, or accelerator at that time. It was already built in 1978, but at that time for high energy physics, and it was also very successful. And the first detection of the gluon, for example. It was then used to pre-accelerate protons and electrons for our largest ring, the Hera, which is already shut down again now. And after the shutdown, this was the opportunity was there to use this ring and rebuild it as a synchrotron radiation source. This has been done starting in 2007, and we started user operation in 2010. The energy is 6 GeV, so it's a high energy storage ring. We provide for the third generation source a really good emittance values. The circumference is one of the reasons for this. It's a large ring, it's 2.3 kilometers in circumference. We are covering a large X-ray energy range, and at the moment we have 23 beamlines in operation. So we have 23 beamlines, as I said. They are now distributed over 3 halls. The largest hall here is the Max von Laue hall, where we host actually 15 beamlines with variable techniques, and we have 2 smaller hutches that have been built a little bit later, which we call the extension project, and there are another 10 beamlines, most of them already working. So the methods at the beamline are very diverse. We are doing scattering, diffraction, spectroscopy, imaging, and coherent applications also, and they are specialized in several parameters. And I should also mention, of course, that we have external contributions. We have 3 beamlines run by the EMBL, 2.5 beamlines by the Helmholtz-Zentrum Geesthacht, and we have an Indian virtual beamline. This means that they have a priority access for about 1.3 beamlines. And we have actually a dedicated Swedish material science beamline, and the Swedish community actually gets about 1.9 beamline equivalents in total. Some statistics in the beginning. So this is the statistics from last year, because as you can imagine, this year was a bit hampered by the COVID-19 crisis. So this is the more kind of a standard year that I'm showing you today. 2019, we had 3,150 unique users, about 6,300 user visits. And as you can see, most of the people are coming actually from Germany. Most than half of the users are coming from Germany, but we have considerable contributions from other countries as well, especially also here, Denmark and Sweden, as you can see. I should mention that this portion usually is higher due to our contract with India, but we had a few issues last year. That's why it has been reduced. This is rather in the 5% range also. Publications also are going up. So we still have people publishing from DORIS. And but DORIS, was the older synchrotron source, was shut down in 2012. And then we have had a little for the extension, we had a little break here. That's why the numbers are so low. But then, as you can see, we are steadily going up with publications and users. I'm sorry. I want just, of course, in this round, I also would like to show you a little bit about the statistic for the Baltic Sea region. So in 2019, we had 593 unique users coming from that region, and you can see the distribution over the different countries here. And a really large part from Sweden is, of course, also due to the fact that the Swedish Research Council is a strategic partner for us and is operating the Swedish material science beamline. We have quite some networking going on in the Baltic Sea region. I would like to mention a few of them. Here is the Baltic Science Network, LEAPS, HALOS, Kremlin Plus, Calypso Plus, Röntgen Angstrom Cluster, Carrots, Baltic Tram, and I apologize for having missed maybe a few of them. We have, of course, also in the region here, many research institutes and universities that we are working together with. Of course, also in Germany, but here I would like to just highlight the international partners from the region, which you can see from, for example, the Aarhus University, Russian Institutes for Accelerator Technology, of course, the KTH in Stockholm, the Swedish Research Council, as I said already. We have cooperations with Lund University, Max 4, and of course, many more. So let me just have a few words on the P21 Beamline, because this is something really special, because it has been funded by the Swedish cooperation partners, and it is basically now operational. I would just like to give you a small update. So we have in principle 3 end stations, 2 inline and 1 side station, where the side station has these parameters, and the techniques here is wide angle X-ray scattering and paired distribution function techniques. And we have more or less empty or available space in EH2, where we can really roll in experiments and equipment instruments that you would like to use. And it's also for very bulky sample environments. And then we have, again, a specialized hutch, which is the third one, which is a diffraction setup with a specialized high energy monochromator. And you can go to time resolution down to milliseconds, and we can use wide angle and small angle scattering and imaging techniques. This is just 2 pictures that shows you that the hutches are really equipped and are in running mode. I don't want to go too much into the details here. But would rather like to show you a few science examples, because of course, PETR3 is doing science in many, many areas. We are going from extreme states of matter to quantum condensed matter, magnetism, superconductivity, materials and processes for energy and transport, nanoscience, information technologies, and of course also a big part is soft matter, health and life science, especially nowadays. I will come back to that in a minute. So here's as I was talking about our cooperation partners, I just like to give 2 examples from the Baltic area. So we have an experiment here led by the KTH in Stockholm about hydrogen infusion in duplex stainless steel. And this was carried out actually at P21. And here they were studying the cathodic hydrogen charging under constant tensile load, and they had the beam coming, recording the scattering under load, and they could then really make a nice depth profile of the lattice spacing, and it has been published recently. This is what they see basically: 20 micrometer depth increments, 1 millimeter translation, scanning procedure, and about 6 minutes per depth scan. A second example is another thing that is led by KTH, by Daniel Söderberg. It's about cellulose-based materials with higher strength fibers. So what you can see here is actually that they were able to design and to build fibers which are really extraordinary strengths. So best strength and stiffness combined with a stiffness to density ratio. So really going to the right corner here. And they could then study these fibers, why they were really producing them in situ at the spinning stage. And what they could really see is then that they could really study the order parameter dependent on the position of these filaments. They could really see how nicely these filaments start to align in the flow process in the fluid. And then I would like to come to a few research, actually 2 research highlights about corona, which we actually, I should mention that at PETR-3, we only had a rather short shutdown at the end of April, or at the beginning of April, and then after about 2 weeks, we already opened again our instruments for corona-related research after we went back in a kind of reduced user service in May. So actually, there was one group coming from the University of Göttingen and other institutions, and they were studying the 3D visual pathohistology of lung tissue from COVID-19 patients. And what they could really see is that around the alveolus, there's a hyaline membrane build, which really causes that these patients suffer from a missing in O2 and CO2 exchange. So these kinds of membranes are the reason why they the exchange of O2 and CO2 is prevented. And this could really be done with a kind of tomography technique at the Beamline P10 at PETR-3, and they could study diameters of 1 millimeter with the resolution of about 170 nanometer. And the second example I would like to mention is a group that studied many proteins, biological molecules that should have the capacity to block a connection point of the virus to the cell. And actually they were studying almost 7,700 different molecules, and they could have, in the end, I think even more than 38 hits where they could show that these molecules would have the possibility to block the active sites. This was a really very much automatized experiment at P11 using the technique of crystallography. And this is also already published. Let me now come to the PETR4 project. As of course you can imagine, this is a really huge and large project that we are planning since some time, and we are just now in the phase of the technical design. And the basic goal of this is, of course, that we want to provide insight and help and science related to the Sustainable Development Goals, of course, that are defined. And we actually can just really do that for many of these goals. We are participating in the regions of health, earth and environment, energy, transport, and information technology with our various techniques. And the good thing with PETR4, or the new thing with PETR4, is that we will be able to really look at all length scales and really start to create and design multifunctional materials which are really tailored local structures, and can basically be built and designed atom by atom, and can be studied also with this resolution. And of course, we are aiming for high resolution, spatial resolution, also time resolution as good as possible. And we are also doing studies in vivo, in operando, and with highest resolution. So how do we do that? We would like to upgrade our ring to a fourth generation source, which has already been done for other sources. Of course, Max 4 is the very good example for this. We already heard about that. So the situation at PETR3 is still that we have a rather extended beam in the horizontal, and already not so bad focused beam in the vertical. But of course, we would like also to go to the situation that we have rather a point source with really exceeded source size and divergence values, where we really have the emittance increased by a factor of 100. And these are the numbers. If you're interested in, I don't compare them to the other sources, but I think this is really nice values, and we have a huge amount of coherence, and up to 10 keV, the beam will be actually fully coherent. So what we have at hand then is that we have really an X-ray microscope for chemical, biological, and physical processes. We can really zoom in to all relevant length scales. We can study chemical, structural, electronic, and magnetic properties of individual nano objects in the macroscopic context. And the dynamics, we can go down at least to the nanosecond scale. So it's a complementary technique, of course, to the X-ray lasers, where you are actually, of course, much faster, as we heard before. So if you look to the difference, to the numbers, what you can see, the value that is always given is the brilliance, the photons in a certain angle and in a certain bandwidth. We are expecting to go up about a factor of 500 in this value in the region around 10 keV, and about a factor 1,000 in the higher energy region. So this means we will have a coherent fraction of the beam at 100 keV that we have now at 10 keV. And as I said, at 10 keV, we are basically fully coherent. And this, of course, gives new opportunities in many fields of science, which were experiments which were on the edge or were not feasible before, are now within the range of being realized. So what could this be? For example, you do nanoprobes, you use the focus nearly full flux in the nano beam. You can basically go from images to movies. You will have a larger field of view. You can go larger field of view, but at the same time, you can solve the needle in the haystack problem. You can really go down to nanometer resolution, especially for coherent imaging. It's very important because the coherent part gives you 4 to 5 orders of magnitude higher coherence flux density. And all these techniques that are spectroscopic and need a lot of flux and are very flux hungry, where you only get a few photons out nowadays, with having 10 to the 13 photons arriving at the sample, they can now also go nano. You can focus your beam basically with the entire intensity. And then these techniques like inelastic X-ray scattering, nuclear resonance scattering, and resonant magnetic scattering can now go to the nanoscale. And also the high energy fraction, of course, is important. You can do things that you couldn't do before because you get more flux and more coherent flux in this energy range. So the spatial resolution, for example, of coherent imaging, you can go down to resolutions below 1 nanometer. Let me give you also an example here. You might want to study cellular complexes in infection research. So you can really go down to visualize the cell structure in very, very high resolution. And you can also, for example, study the distribution of different elements with nanometer resolution. The second thing is, for example, energy materials, where you usually have applications like batteries, fuel cells, catalysts that you would like to study in operando, for example, and under charge or decharge conditions. And you can not only do that using imaging now, but you can also use now spectroscopy techniques to really see the difference in the electronic structure by using X-rays, which of course have the advantage, or high energy X, which have the advantage to penetrate materials while they are working. So to look inside a battery is very difficult with visible or low energy light, of course. The project timeline for PETR4 is we are somewhere here. So we already finished the CDR phase. The CDR report is ready. You can get a copy. Just let us know. No problem. You can also download it from our websites. We are now in the PETR4 TDR phase. And actually, this phase goes at least up to 2022, end of 2022, where we then would like to start the project phase. And if everything goes fine, we would like to start PETR4 operation in 2027. These timescales, of course, have not yet been adapted to all the things related to the COVID-19 crisis. But at the moment, we are still planning in this way. So what is the Beamline, or the next step? What we are doing now is to define the Beamline portfolio. And this is, of course, one of the work packages for the TDR, where we really would like to get all the experts together and all the ideas, especially together, and develop a new Beamline portfolio, which consists of about 30 Beamlines. And of course, the important parameters are the science drivers for PETR4 that we are collecting. We will also take into account the resulting experimental requirements, boundary conditions from the new machine, and of course, the existing Beamline portfolio. And in the end, what PETR4 should look like is that we keep our 3 halls that we already have here, down here, and we will have a huge, large hall, an opposite position to the Max von Laue hall on the other side of the ring, where we again can host another 14 Beamlines, or even up to 16. And what we are doing now is actually, we are in this phase, we are preparing and collecting the scientific instrument proposals. And this call is open, and it is the deadline for this is the 1st of December. We are collecting that from facilities and users, and basically everybody who has a brilliant idea how to use the new opportunities at PETR4 can hand in such a scientific instrument proposal. And we also have user workshops defining the experimental requirements on different aspects. I will come back to this later. And actually, these workshops just started and they're about to run. And here they are. So we just had the first one, and we are going to have the next one on soft matter on the 28th of October. And you see that there's another one for earth and volatile material nanoscience in November, and then finally one on the technical challenges and scientific computing. So basically, if you are interested, and we are of course very open, and we need your input. So please use this opportunity, take the chance to make your science ideas part of the scientific instrument proposals. As I said, the deadline is the 1st of December. And all I can say is that we should keep working together. And I thank you very much for your attention. And also thanks to the PETRA staff and the city of Hamburg. And this is the view of PETR3 and the new project of the Science City Hamburg-Bahrenfeld, the newest and latest project of the Hamburg city, where we hope to be one of important parts. Thank you very much.
Thank you. Thank you very much, Hans Christian. And we have a couple of questions. The first one is, how do I get access to P21 as non-Swede? And maybe we can open this question a bit more up. Could you give overall comment on access and applications in your facilities?
Yes, of course. I should have mentioned this. Yes. So it is pretty much the same as at Max 4 or other synchrotron radiation sources. We have, of course, the absolute majority and main part of our user program is given by a peer review access. So anybody in the world can write a proposal it will be peer-reviewed by external experts, and then it will be given a ranking, and depending on the overbooking and the quality of your proposal, you will get beam time. So it is absolutely not necessary to be part of any of our priority access partners. This is only a very small fraction. And of course, we have the possibility also to give beam time to industrial users, where the industrial users, the same as at Max 4, they basically pay for the beam time and they're not obliged to publish the results in the end.
Thank you. We have interesting question considering timeline. What can I do at Flash and Petra next year, or do I have to wait for PETR4?
You can do many things at PETR3 and at Flash actually, and you don't have to wait for PETR4. But of course, there are a few cases where you might have to wait, and if you have an idea for an experiment that you cannot already do at these sources, please get in touch with us and maybe also hand in a scientific instrument proposal. So the machines are running. We are in user service. We have many opportunities. If you'd like to know more, just please get in touch with us. Of course, you can do anything, many things already.
Many things already. We have a question considering COVID-19. Are there any kind of limitations at a particular moment that especially you have to think considering application and access in Petra?
Well, we of course have adapted our user service and our user, also the access a little bit to the situation. So we of course following a strict every and all official corona-related measures given from, of course, indicated by the government, and we are having even stronger safety rules on site. One of the things that has changed for the users, for example, is that they, starting actually from today on, have to provide a negative corona test. And the usual experiments are restricted to 3 external users. So if you have an experiment that needs more than 3 external users coming to our campus, you really have to ask for it in advance and you need to get a permission. Otherwise, the usual rules adapt, of course. So we're keeping distance, we're wearing masks, and we're trying to operate as safe as possible. And so far, there is no official shutdown. The numbers are increasing. We are watching this on a daily basis, and we are, of course, informing our users about changes of the rules immediately. But at the moment, the only real big difference is, of course, besides following all the usual corona rules, is that you cannot come to the experiment with more than 3 people in general.
Thank you very much, Hans Christian from DESY, Germany. Have a nice day.